Chapter 3 Motion in a Straight Line 3.1 Introduction 3.2 Position, Path Length, and Displacement 3.3 Average Velocity and Average Speed 3.4 Instantaneous Velocity and Speed 3.5 Acceleration 3.6 Kinematic Equations for Uniformly Accelerated Motion 3.7 Relative Velocity Summary Points to Ponder Exercises Additional Exercises Appendix 3.1 3.1 Introduction Motion is common to everything in the universe. We walk, run, and ride a bicycle. Even when we are sleeping, air moves into and out of our lungs and blood flows in arteries and veins. We see leaves falling from trees and water flowing down a dam. Automobiles and planes carry people from one place to the other. The Earth rotates once every 24 hours and revolves round the Sun once in a year. The Sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. Motion is change in position of an object with time. How does the position change with time? In this chapter, we shall learn how to describe motion. For this, we develop the concepts of velocity and acceleration. We shall confine ourselves to the study of motion of objects along a straight line, also known as rectilinear motion. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. In our discussions, we shall treat the objects in motion as point objects. This approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. In kinematics, we study ways to describe motion without going into the causes of motion. What causes motion described in this chapter and the next chapter forms the subject matter of Chapter 5. 3.2 Position, Path Length, and Displacement. Earlier you learned that motion is change in position of an object with time. In order to specify position, we need to use a reference point and a set of axes. It is convenient to choose 4D physics a rectangular coordinate system consisting of three mutually perpendicular axes, labeled x, y, and z axes. The point of intersection of these three axes is called origin, O, and serves as the reference point. The coordinates, x, y, z, of an object describe the position of the object with respect to this coordinate system. To measure time, we position a clock in this system. This coordinate system along with a clock constitutes a frame of reference. If one or more coordinates of an object change with time, we say that the object is in motion. Otherwise, the object is said to be at rest with respect to this frame of reference. The choice of a set of axes in a frame of reference depends upon the situation. For example, for describing motion in one dimension, we need only one axis. To describe motion in 2/3 dimensions, we need a set of 2/3 axes. Description of an event depends on the frame of reference chosen for the description. For example, when you say that a car is moving on a road, you are describing the car with respect to a frame of reference attached to you or to the ground. But with respect to a frame of reference attached with a person sitting in the car is at rest. To describe motion along a straight line, we can choose an axis, say x-axis, so that it coincides with the path of the object. We then measure the position of the object with reference to a conveniently chosen origin, say O, as shown in Fig 3.1. Positions to the right of O are taken as positive and to the left of O, as negative. Following this convention, the position coordinates of point P and Q in Fig 3.1 are plus 360 m and plus 240 m. Similarly, the position coordinate of point R is 120 m. Path length. Consider the motion of a car along a straight line. We choose the x-axis such that it coincides with the path of the car's motion and origin of the axis as the point from where the car started moving, i.e. the car was at x equals 0 at t equals 0, Fig 3.1. Let P, Q, and R represent the positions of the car at different instants of time. Consider two cases of motion. In the first case, the car moves from O to P. then the distance moved by the car is OP equals plus 360 m. This distance is called the path length traversed by the car. In the second case, the car moves from O to P and then moves back from P to Q. During this course of motion, the path length traversed is OP plus PQ equals plus 360 m plus 120 m, equals plus 480 m. Path length is a scalar quantity, a quantity that has a magnitude only and no direction, see Chapter 4. Displacement. It is useful to define another quantity, displacement, as the change in position. Let x1 and t x be 2 then the positions of an object at time t. Its displacement, denoted by x1 in time 2 tons equals t is given by the difference 1 between the final and initial positions, x equals xx. We use the Greek 1 letter delta to denote a change in a quantity. If x is positive, and if x is 1 negative. Displacement has both magnitude and direction. Such quantities are represented by vectors. You will read about vectors in the next chapter. Presently, we are dealing with motion along a straight line, also called rectilinear motion, only. In one-dimensional motion, there are only two directions, backward and forward, upward and downward, in which an object can move, and these two directions can easily be specified by and signs. For example, displacement of the car in moving from O to P is x equals xx equals plus 360 m, 0 m equals plus 360 m to 1. The displacement has a magnitude of 360 m and is directed in the positive x direction as indicated by the plus sign. Similarly, the displacement of the car from P to Q is 240 m. 360 m equals 120 m. The Fig 3.1 x-axis, origin and positions of a car at different times. Motion in a straight line. 41 negative sign indicates the direction of displacement. Thus, it is not necessary to use vector notation for discussing motion of objects in one dimension. The magnitude of displacement may or may not be equal to the path length traversed by an object. For example, for motion of the car from O to P, the path length is plus 360 m and the displacement is plus 360 m. In this case, the magnitude of displacement, 360 m, is equal to the path length, 360 m. But consider the motion of the car from O to P and back to Q. In this case, the path length equals, plus 360 m, plus 120 m, equals plus 480 m. However, the displacement equals, plus 240 m, 0 m, equals plus 240 m. Thus, the magnitude of displacement, 240 m, is not equal to the path length, 480 m. The magnitude of the displacement for a course of motion may be 0 but the corresponding path length is not 0. For example, if the car starts from O, goes to P and then returns to O, the final position coincides with the initial position and the displacement is 0. However, the path length of this journey is OP plus PO equals 360 m plus 360 m equals 720 m. Motion of an object can be represented by a position-time graph as you have already learned about it. Such a graph is a powerful tool to represent and analyze different aspects of motion of an object. For motion along a straight line, say x-axis, only x-coordinate varies with time and we have an xt graph. Let us first consider the simple case in which an object is stationary, e.g. a car standing still at x equals 40 m. The position-time graph is a straight line parallel to the time axis, as shown in Fig 3.2, a. If an object moving along the straight line covers equal distances in equal intervals of time, it is said to be in uniform motion along a straight line. Fig 3.2, b, shows the position-time graph of such a motion. Fig 3.2 position-time graph of a. Stationary object, and b. An object in uniform motion. X, m, t, s, Fig 3.3 Position time graph of a car. 42 Physics. Now, let us consider the motion of a car that starts from rest at time t equals 0s from the origin O and picks up speed till t equals 10s and thereafter moves with uniform speed till t equals 18s. Then the brakes are applied and the car stops at t equals 20s and x equals 296 m. The position time graph for this case is shown in Fig 3.3. We shall refer to this graph in our discussion in the following sections. 3.3 Average velocity and average speed. When an object is in motion, its position changes with time. But how fast is the position changing with time and in what direction? To describe this, we define the quantity average velocity. Average velocity is defined as the change in position or displacement, x, divided by the time intervals, t, in which the displacement occurs, v equals x2, x1 equals xt2, t1 t3.1, where x2 and x1 are the positions of the object at time t2a and dt1, respectively. Here the bar over the symbol for velocity is a standard notation used to indicate an average quantity. The SI unit for velocity is m/s or ms1, although kmh1 is used in many everyday applications. Like displacement, average velocity is also a vector quantity. But as explained earlier, for motion in a straight line, the directional aspect of the vector can be taken care of by and signs, and we do not have to use the vector notation for velocity in this chapter. Fig 3.4 The average velocity is the slope of line pp. 12 Consider the motion of the car in Fig 3.3. The portion of the xt graph between t equals 0s and t equals 8s is blown up and shown in Fig 3.4. As seen from the plot, the average velocity of the car between time t equals 5s and t equals 7s is, v equals x2 t2, x1, t1 equals, 27.4 to 10.0, m, 7 to 5, s equals 8.7 ms1. Geometrically, this is the slope of the straight line p1 p2 connecting the initial position p1 to the final position p2 as shown in Fig 3.4. The average velocity can be positive or negative depending upon the sign of the displacement. It is 0 if the displacement is 0. Fig 3.5 shows the xt graphs for an object, moving with positive velocity, Fig 3.5a, moving with negative velocity, Fig 3.5b, and at rest, Fig 3.5c. Fig 3.5 Position time graph for an object, a, moving with positive velocity, b, moving with negative velocity, and c, at rest. Average velocity as defined above involves only the displacement of the object. We have seen earlier that the magnitude of displacement may be different from the actual path length. To describe the rate of motion over the actual path, we introduce another quantity called average speed. Average speed is defined as the total path length traveled divided by the total time interval during which the motion has taken place. Total path length average speed equals total time interval. 3.2 Average speed has obviously the same unit, ms1, as that of velocity. But it does not tell us in what direction an object is moving. Thus, it is always positive, in contrast to the average velocity which can be positive or negative. If the motion of an object is along a straight line and in the same direction, the magnitude of displacement is equal to the total path length. In that case, the magnitude of average velocity motion in a straight line 43 is equal to the average speed. This is not always the case, as you will see in the following example. Example 3.1 A car is moving along a straight line, say OP in Fig 3.1. It moves from O to P in 18s and returns from P to Q in 6.0s. What are the average velocity and average speed of the car in going, A, from O to P, and, B, from O to P and back to Q? Answer, A. Displacement average velocity equals time interval v equals plus 360 m equals plus 20 ms1 18s path length average speed equals time interval equals 360 m equals 20 ms1 18s. Thus, in this case the average speed is equal to the magnitude of the average velocity. b. In this case, average velocity equals displacement time interval equals plus 240 m, 18 plus 6.0, s equals plus 10 m s1 average speed equals path length equals op plus pq time interval t, 360 plus 120, equals m equals 20 ms1 24 s 3.4 Instantaneous velocity and speed. The average velocity tells us how fast an object has been moving over a given time interval but does not tell us how fast it moves at different instants of time during that interval. For this, we define instantaneous velocity or simply velocity v at an instant t. The velocity at an instant is defined as the limit of the average velocity as the time interval t becomes infinitesimally small. In other words, xv equals lim t0 tons, 3.3a, dx equals dt, 3.3b, where the symbol lim t0 stands for the operation of taking limit as t0 of the quantity on its right. In the language of calculus, the quantity on the right-hand side of eq, 3.3a, is the differential coefficient of x with respect to t, and dx is denoted by, see Appendix 3.1. It is the dt rate of change of position with respect to time, at that instant. We can use eq, 3.3a, for obtaining the value of velocity at an instant either graphically or numerically. Suppose that we want to obtain graphically the value of velocity at time t equals 4s, point p, for the motion of the car represented in Fig 3.3. The figure has been redrawn in Fig 3.6 choosing different scales to facilitate the thus. In this case the average speed is not equal to the magnitude of the average velocity. This happens because the motion here involves change in direction so that the path length is greater than the magnitude of displacement. This shows that speed is, in general, greater than the magnitude of the velocity. If the car in example 3.1 moves from O to P and comes back to O in the same time interval, average speed is 20 m/s but the average velocity is 0. Fig 3.6 Determining velocity from position time graph. Velocity at t equals 4s is the slope of the tangent to the graph at that instant. 44 Physics calculation. Let us take t equals 2s centered at t equals 4s. Then, by the definition of the average velocity, the slope of line p1 p2, Fig 3.6, gives the value of average velocity over the interval 3s to 5s. Now, we decrease the value of t from 2s to 1s. Then line p1 p2 becomes q1 q2 and its slope gives the value of the average velocity over the interval 3.5s to 4.5s. In the limit t0, the line p1 p2 becomes tangent to the position time curve at the point p and the velocity at t equals 4s is given by the slope of the tangent at that point. It is difficult to show this process graphically. But if we use numerical method to obtain the value of the velocity, the meaning of the limiting process becomes clear. For the graph shown in Fig 3.6, x equals 0.08 t3. Table 3.1 gives the value of x/t calculated for t equal to 2.0s, 1.0s, 0.5s, 0.1s, and 0.01s centered at t equals 4.0s. The second and third columns give the value of t1 equals t, 2 and t2 equals t plus 2, and the fourth and the fifth columns give the corresponding values of x, i.e. x, t1, equals 0.08 t13 and x, t2, equals 0.08 t23. The sixth column lists the difference x equals x, t2, x, t1, and the last column gives the ratio of x and t, i.e. the average velocity corresponding to the value of t listed in the first column. We see from table 3.1 that as we decrease the value of t from 2.0s to 0.010s, the value of the average velocity approaches the limiting value 3.84 ms1, which is the value of velocity at dxt equals 4.0s, i.e. the value of at t equals 4.0s. In this dt manner, we can calculate velocity at each instant for motion of the car shown in Fig 3.3. For this case, the variation of velocity with time is found to be as shown in Fig 3.7. Fig 3.7 Velocity time graph corresponding to motion shown in Fig 3.3. The graphical method for the determination of the instantaneous velocity is always not a convenient method. For this, we must carefully plot the position time graph and calculate the value of average velocity as t becomes smaller and smaller. It is easier to calculate the value of velocity at different instants if we have data of positions at different instants or exact expression for the position as a function of time. Then, we calculate x/t from the data for decreasing the value of t and find the limiting value as we have done in Table 3.1, or use differential calculus for the given expression and dx calculate at different instants as done in dt. The following example. X Table 3.1 limiting value of t at t equals 4s motion in a straight line 45. Example 3.2 The position of an object moving along x-axis is given by x equals a plus b t2, where a equals 8.5 m, b equals 2.5 m s2 and t is measured in seconds. What is its velocity at t equals 0 s and t equals 2.0 s? What is the average velocity between t equals 2.0 s and t equals 4.0 s? Answer. In notation of differential calculus, the velocity is dxv equals dA plus bt2 equals 2bt equals 5.0 tons ms1 dt at t equals 0 s, v equals 0 ms1 and at t equals 2.0 s, v equals 10 ms1. Average velocity equals x, 4.0, x, 2.0, 4.0 to 2.0 equals a plus 1/6 b a 4 b equals 6.0 times b 2.0 equals 6.0 times 2.5 equals 15 ms1. From Fig 3.7, we note that during the period t equals 10s to 18s the velocity is constant. Between period t equals 18s to t equals 20s, it is uniformly decreasing, and during the period t equals 0s to t equals 10s, it is increasing. Note that for uniform motion, velocity is the same as the average velocity at all instants. Instantaneous speed, or simply speed, is the magnitude of velocity. For example, a velocity of plus 24.0 ms1 and a velocity of 24.0 ms1 both have an associated speed of 24.0 ms1. It should be noted that though average speed over a finite interval of time is greater or equal to the magnitude of the average velocity, instantaneous speed at an instant is equal to the magnitude of the instantaneous velocity at that instant. Why so? 3.5 Acceleration. The velocity of an object, in general, changes during its course of motion. How to describe this change? Should it be described as the rate of change in velocity with distance or with time? This was a problem even in Galileo's time. It was first thought that this change could be described by the rate of change of velocity with distance. But, through his studies of motion of freely falling objects and motion of objects on an inclined plane, Galileo concluded that the rate of change of velocity with time is a constant of motion for all objects in free fall. On the other hand, the change in velocity with distance is not constant, it decreases with the increasing distance of fall. This led to the concept of acceleration as the rate of change of velocity with time. The average acceleration over a time interval is defined as the change of velocity divided by the time interval, a equals v2 v1 equals vt2 t1 t. 3.4, where v2 and v1 are the instantaneous velocities, or simply velocities at time t2 and t1. It is the average change of velocity per unit time. The SI unit of acceleration is ms2. On a plot of velocity versus time, the average acceleration is the slope of the straight line connecting the points corresponding to v2, t2, and v1, t1. The average acceleration for velocity time graph shown in Fig 3.7 for different time intervals 0s, 10s, 10s 18s, and 18s 20s are 0s, 10s a equals 24, 10 0, ms 0, s1 equals 2.4 ms2 10s, 18s a equals 24, 18 24, ms 10, s1 equals 0 ms2 18s, 20 sa equals 0 24, m, 2018, S1s equals 12 ms2a, ms2, Fig 3.8 acceleration as a function of time for motion represented in Fig 3.3. Instantaneous acceleration is defined in the same way as the instantaneous velocity, a equals lim v equals dvt 0 tons dt, 3.5, the acceleration at an instant is the slope of the tangent to the vt curve at that instant. For the vt curve shown in Fig 3.7, we can obtain acceleration at every instant of time. The resulting AT curve is shown in Fig 3.8. We see 46 physics that the acceleration is non-uniform over the period 0s to 10s. It is 0 between 10s and 18s and is constant with value 1 to ms2 between 18s and 20s. When the acceleration is uniform, obviously, it equals the average acceleration over that period. Since velocity is a quantity having both magnitude and direction, a change in velocity may involve either or both of these factors. Acceleration, therefore, may result from a change in speed, magnitude, a change in direction or changes in both. Like velocity, acceleration can also be positive, negative, or zero. Position time graphs for motion with positive, negative, and zero acceleration are shown in Figs 3.9, A, B, and C, respectively. Note that the graph curves upward for positive acceleration, downward for negative acceleration, and it is a straight line for zero acceleration. As an exercise, identify in Fig 3.3, the regions of the curve that correspond to these three cases. Although acceleration can vary with time, our study in this chapter will be restricted to motion with constant acceleration. In this case, the average acceleration equals the constant value of acceleration during the interval. If the velocity of an object is v at t equals 0 and v at time t, we have a equals v, v0 t minus 0 or, v equals v0 plus at, 3.6, b, an object is moving in positive direction with a negative acceleration, for example, motion of the car in Fig 3.3 between t equals 18s and 20s, c, an object is moving in negative direction with a negative acceleration, for example the motion of a car moving from O in Fig 3.1 in negative x direction with increasing speed. D, an object is moving in positive direction till time t1, and then turns back with the same negative acceleration, for example the motion of a car from point O to point Q in Fig 3.1 till time t1 with decreasing speed and turning back and moving with the same negative acceleration. An interesting feature of a velocity time graph for any moving object is that the area under the curve represents the displacement over a given time interval. A general proof of this Fig 3.9 position time graph for motion with a. positive acceleration, b. negative acceleration, and c. zero acceleration. Let us see how velocity time graph looks like for some simple cases. Fig 3.10 shows velocity time graph for motion with constant acceleration for the following cases. A. An object is moving in a positive direction with a positive acceleration, for example the motion of the car in Fig 3.3 between t equals 0s and t equals 10s. Fig 3.10 velocity time graph for motions with constant acceleration. A. Motion in positive direction with positive acceleration, b. Motion in positive direction with negative acceleration, c. Motion in negative direction with negative acceleration, d. Motion of an object with negative acceleration that changes direction at time t1. Between times 0 to t1, it moves in positive x direction, and between t1 and t2 it moves in the opposite direction. Motion in a straight line 47 statement requires use of calculus. We can, however, see that it is true for the simple case of an object moving with constant velocity u. Its velocity time graph is as shown in Fig 3.11. Equals 1 2, v0, t plus v0 t. Fig 3.11 area under vt curve equals displacement of the object over a given time interval. The vt curve is a straight line parallel to the time axis, and the area under it between t equals 0 and t equals t is the area of the rectangle of height u and base t. Therefore, area equals u times t equals ut, which is the displacement in this time interval. How come in this case an area is equal to a distance? Think. Note the dimensions of quantities on the two coordinate axes, and you will arrive at the answer. Note that the xt, vt, and at graphs shown in several figures in this chapter have sharp kinks at some points, implying that the functions are not differentiable at these points. In any realistic situation, the functions will be differentiable at all points and the graphs will be smooth. What this means physically is that acceleration and velocity cannot change values abruptly at an instant. Changes are always continuous. 3.6 Kinematic equations for uniformly accelerated motion. For uniformly accelerated motion, we can derive some simple equations that relate displacement, x, time taken, t, initial velocity, v0, final velocity, v, and acceleration, a. Equation 3.6, already obtained, gives a relation between final and initial velocities v and v0 of an object moving with uniform acceleration a, v equals v0 plus at 3.6. This relation is graphically represented in Fig 3.12. The area under this curve is area between instants 0 and t equals area of triangle ABC plus area of rectangle OACD. Fig 3.12. Area under VT curve for an object with uniform acceleration. As explained in the previous section, the area under VT curve represents the displacement. Therefore, the displacement x of the object is x equals 1 2 v0 t plus v0 t, but v0 equals at. Therefore, x equals 1 a2 t2 plus v0 t, or x equals v0 t plus 1 2 at 2. Equation 3.7 can also be written as x equals v plus v0 t equals vt2, where 3.7, 3.8, 3.9a, v equals v plus v0, constant acceleration only, 2, 3.9b, equations 3.9a and 3.9b mean that the object has undergone displacement x with an average velocity equal to the arithmetic average of the initial and final velocities. From EQ 3.6, t equals v0 slash a. Substituting this in EQ 3.9a, we get x equals vt equals v plus v0 2v, v0a equals v2, v0 2 2a, v2 equals v0 2 plus 2ax. 3.10, 48 Physics. This equation can also be obtained by substituting the value of t from EQ 3.6 into EQ 3.8. Thus, we have obtained three important equations: v equals v0 plus at x equals v0 t plus 1 at 2 2, v2 equals v0 2 plus 2ax. 3.11a, connecting five quantities v0, v, a, t and x. These are kinematic equations of rectilinear motion for constant acceleration. The set of EQ 3.11a were obtained by assuming that at t equals 0, the position of the particle, x, is 0. We can obtain a more general equation if we take the position coordinate at t equals 0 as non-zero, say x0. Then x 3.11a are modified, replacing x by x0, 2, v equals v0 plus at x equals x0 plus v0 t plus 1 at 2 2. 3.11b, v2 equals v0 2 plus 2a, x, x0. 3.11c, example 3.3. Obtain equations of motion for constant acceleration using method of calculus. Answer by definition: a equals dv dt, dv equals a dt integrating both sides, vt dv equals a dt, v0 0 tons equals a dt 0, v0 equals at v equals v0 plus at. Further, v equals dx dt, dx equals v dt integrating both sides, xt dx equals v dt x0 0, a is constant, equals t0 v0 plus at dt x0 equals v0 t plus 1 at 2 t2 x equals x0 plus v0 t plus 1 2 at t2. We can write a equals dv equals dv dx equals v dv dt dx dt dx, or v dv equals a dx integrating both sides, Vx v dv equals a dx v0 x0 v2 v0 2 2 equals a, x x0, v2 equals v0 2 plus 2a, x x0. The advantage of this method is that it can be used for motion with non-uniform acceleration also. Now, we shall use these equations to some important cases. Example 3.4. A ball is thrown vertically upwards with a velocity of 20 ms1 from the top of a multi-story building. The height of the point from where the ball is thrown is 25.0 m from the ground. A. How high will the ball rise? And, B. How long will it be before the ball hits the ground? Take g equals 10 ms2. Answer, A. Let us take the y-axis in the vertically upward direction with 0 at the ground, as shown in Fig 3.13. Now v equals plus 20 ms1, OA equals g equals 10 ms2, v equals 0 ms1 if the ball rises to height y from the point of launch. Then using the equation, v2 equals v0 2 plus 2a y0 we get 0 equals, 20, 2 plus 2, 10, y0, solving, we get, y0, equals 20 m, b. We can solve this part of the problem in two ways. Note carefully the methods used. Motion in a straight line 49 0 equals 25 plus 20 tons plus, 1/2, minus 10, t2 or, 5 t2 20 tons 25 equals 0. Solving this quadratic equation for t, we get t equals 5. Note that the second method is better since we do not have to worry about the path of the motion as the motion is under constant acceleration. Example 3.5. Free fall. Discuss the motion of an object under free fall. Neglect air resistance. Fig 3.13. First method. In the first method, we split the path in two parts, the upward motion, A to B, and the downward motion, B to C, and calculate the corresponding time taken t1 and t2. Since the velocity at B is 0, we have, v equals vo plus at 0 equals 21 0 t1 or, t1 equals 2s. This is the time in going from A to B. From B, or the point of the maximum height, the ball falls freely under the acceleration due to gravity. The ball is moving in negative y direction. We use equation y equals y0 plus v0 t plus 1 2 at 2 we have, y0 equals 45 m, y equals 0, v0 equals 0, a equals g equals 10 ms2 0 equals 45 plus, 1/2, 10, t2 2 solving, we get t2 equals 3s. Therefore, the total time taken by the ball before it hits the ground equals t1 plus t2 equals 2s plus 3s equals 5s. Second method, the total time taken can also be calculated by noting the coordinates of initial and final positions of the ball with respect to the origin chosen and using equation y equals y0 plus v0 t plus 1 at 2 2. Now y0 equals 25 m, y equals 0 m, vo equals 20 ms1, a equals 10 ms2, t equals. Answer: an object released near the surface of the Earth is accelerated downward under the influence of the force of gravity. The magnitude of acceleration due to gravity is represented by g. If air resistance is neglected, the object is said to be in free fall. If the height through which the object falls is small compared to the Earth's radius, g can be taken to be constant, equal to 9.8 ms2. Free fall is thus a case of motion with uniform acceleration. We assume that the motion is in y direction, more correctly in y direction because we choose upward direction as positive. Since the acceleration due to gravity is always downward, it is in the negative direction and we have a equals g equals 9.8 ms2. The object is released from rest at y equals 0. Therefore, v0 equals 0 and the equations of motion become, v equals 0 gt equals 9.8 t ms1 y equals 0 half a gram t2 equals 4.9 t2 m v2 equals 0.2 grams y equals 19.6 y m2 s2. These equations give the velocity and the distance traveled as a function of time and also the variation of velocity with distance. The variation of acceleration, velocity, and distance, with time have been plotted in Fig 3.14, A, B, and C. A. 50 physics traversed during successive intervals of time. Since initial velocity is 0, we have y equals 1 gt22. Using this equation, we can calculate the position of the object after different time intervals, 0, 2, 3, which are given in second column of table 3.2. If we take 1/2, g2 as y0, the position coordinate after first time interval, then third column gives b, the positions in the unit of yo. The fourth column gives the distances traversed in successive s. We find that the distances are in the simple ratio 1, 3, 5, 7, 9, 11. As shown in the last column. This law was established by Galileo Galilei, 1564 to 1642, who was the first to make quantitative studies of free fall. See Fig 3.14. Motion of an object under free fall. A. Variation of acceleration with time. B. Variation of velocity with time. C. Variation of distance with time. Example 3.6. Galileo's law of odd numbers. The distances traversed, during equal intervals of time, by a body falling from rest, stand to one another in the same ratio as the odd numbers beginning with unity, namely, 1, 3, 5, 7. Prove it. Example 3.7. Stopping distance of vehicles. When brakes are applied to a moving vehicle, the distance it travels before stopping is called stopping distance. It is an important factor for road safety and depends on the initial velocity, v0, and the braking capacity, or deceleration, a, that is caused by the braking. Derive an expression for stopping distance of a vehicle in terms of VO and A. Answer: let the distance traveled by the vehicle before it stops be ds. Then, using equation of motion v2 equals VO2 plus 2x, and noting that v equals 0, we have the stopping distance. Answer: let us divide the time interval of motion of an object under free fall into many equal intervals and find out the distances. Thus, the stopping distance is proportional to the square of the initial velocity. Doubling the table 3.2. Motion in a straight line. 51. Initial velocity increases the stopping distance by a factor of 4, for the same deceleration. For the car of a particular make, the braking distance was found to be 10 m, 20 m, 34 m, and 50 m, corresponding to velocities of 11, 15, 20 and 25 m/s, which are nearly consistent with the above formula. Stopping distance is an important factor considered in setting speed limits, for example, in school zones. Example 3.8. Reaction time. When a situation demands our immediate action, it takes some time before we really respond. Reaction time is the time a person takes to observe, think, and act. For example, if a person is driving and suddenly a boy appears on the road, then the time elapsed before he slams the brakes of the car is the reaction time. Reaction time depends on complexity of the situation and on an individual. You can measure your reaction time by a simple experiment. Take a ruler and ask your friend to drop it vertically through the gap between your thumb and forefinger, Fig 3.15. After you catch it, find the distance d traveled by the ruler. In a particular case, d was found to be 21.0 centimeters. Estimate reaction time. Fig 3.15. Measuring the reaction time. Answer: the ruler drops under free fall. Therefore, VO equals 0, and g equals 9.8 ms2. The distance traveled d and the reaction time tr are related by d equals 1/2 gtr2 or tr equals 2 dsg. Given d equals 21.0 centimeters and g equals 9.8 ms2, the reaction time is tr equals 2 times 0.21 s 0.2 s 9.8 3.7. Relative velocity. You must be familiar with the experience of traveling in a train and being overtaken by another train moving in the same direction as you are. While that train must be traveling faster than you to be able to pass you, it does seem slower to you than it would be to someone standing on the ground and watching both the trains. In case both the trains have the same velocity with respect to the ground, then to you the other train would seem to be not moving at all. To understand such observations, we now introduce the concept of relative velocity. Consider two objects A and B moving uniformly with average velocities VA and VB in one dimension, say along x-axis. Unless otherwise specified, the velocities mentioned in this chapter are measured with reference to the ground. If xa, 0, and xb, 0, are positions of objects A and B, respectively at time t equals 0, their positions xa, t, and xb, t, at time t are given by xa, t, equals xa, 0, plus vat xb, t, equals xb, 0, plus vbt, 3.12a, 3.12b, then, the displacement from object A to object B is given by xba, t, equals xb, t, xa, t, equals xb, 0, xa, 0, plus, vbva, t, 3.13, equation, 3.13, is easily interpreted. It tells us that as seen from object A, object B has a velocity vbva because the displacement from A to B changes steadily by the amount vbva in each unit of time. We say that the velocity of object B relative to object A is vbva, v equals vvbaba, 3.14a, similarly, velocity of object A relative to object B is, vab equals vavb, 3.14b, 52 Physics Fig 3.16 Position time graphs of two objects with equal velocities. This shows, VBA equals VAB, 3.14c, now we consider some special cases, a, if VB equals VA, VBVA equals 0. Then, from EQ, 3.13, XB, T, XA, T, equals XB, 0, XA, 0. Therefore, the two objects stay at a constant distance, xb, 0, xa, 0, apart, and their position time graphs are straight lines parallel to each other as shown in Fig 3.16. The relative velocity VAB or VBA is 0 in this case. B, if VAVB, VBVA is negative. One graph is steeper than the other and they meet at a common point. For example, suppose VA equals 20 ms1 and XA, 0, equals 10 m, and VB equals 10 ms1, XB, 0, equals 40 m, then the time at which they meet is t equals 3s, Fig 3.17. At this instant they are both at a position XA, t, equals XB, t, equals 70 m. Thus, object A overtakes object B at this time. In this case VBA equals 10 ms1 20 ms1 equals 10 ms1 equals VAB. C. Suppose VA and VB are of opposite signs. For example, if in the above example object A is moving with 20 ms1 starting at XA, 0, equals 10 m and object B is moving with 10 ms1 starting at XB, 0, equals 40 m, the two objects meet at t equals 1s, Fig 3.18. The velocity of B relative to A, VBA equals 10, 20, ms1 equals 30 ms1 equals VAB. In this case, the magnitude of VBA or VAB, equals 30 ms1, is greater than the magnitude of velocity of A or that of B. If the objects under consideration are two trains, then for a person sitting on either of the two, the other train seems to go very fast. Note that EQ, 3.14, are valid even if VA and VB represent instantaneous velocities. Fig 3.17 Position time graphs of two objects with unequal velocities, showing the time of meeting. T, S, Fig 3.18 Position time graphs of two objects with velocities in opposite directions, showing the time of meeting. Example 3.92 Parallel rail tracks run north-south. Train A moves north with a speed of 54 km h1, and train B moves south with a speed of 90 km h1. What is the A. velocity of B with respect to A, B. velocity of ground with respect to B, and C. velocity of a monkey running on the roof of the train A against its motion, with a velocity of 18 km h1 with respect to the train A, as observed by a man standing on the ground? Answer: choose the positive direction of x-axis to be from south to north. Then, motion in a straight line 53 VA equals plus 54 kilometers h1 equals 15 ms1 VB equals 90 kilometers h1 equals 25 ms1 relative velocity of B with respect to A equals VB VA equals 40 ms1, i.e. the train B appears to A to move with a speed of 40 ms1 from north to south. Relative velocity of ground with respect to B equals 0 VB equals 25 ms1. In C, let the velocity of the monkey with respect to ground be Vm. Relative velocity of the monkey with respect to A, Vma equals Vm Va equals 18 km h1 equals 5 ms1. Therefore, Vm equals 15.5, ms1 equals 10 ms1. Summary 1. An object is said to be in motion if its position changes with time. The position of the object can be specified with reference to a conveniently chosen origin. For motion in a straight line, position to the right of the origin is taken as positive and to the left as negative. 2. Path length is defined as the total length of the path traversed by an object. 3. Displacement is the change in position, x equals x2 x1. Path length is greater or equal to the magnitude of the displacement between the same points. 4. An object is said to be in uniform motion in a straight line if its displacement is equal in equal intervals of time. Otherwise, the motion is said to be non-uniform. 5. Average velocity is the displacement divided by the time interval in which the displacement occurs, xv equals t on an xt graph. The average velocity over a time interval is the slope of the line connecting the initial and final positions corresponding to that interval. 6. Average speed is the ratio of total path length traversed and the corresponding time interval. The average speed of an object is greater or equal to the magnitude of the average velocity over a given time interval. 7. Instantaneous velocity or simply velocity is defined as the limit of the average velocity as the time interval t becomes infinitesimally small, v equals lim x equals dxt 0 tons dt. The velocity at a particular instant is equal to the slope of the tangent drawn on position time graph at that instant. 8. Average acceleration is the change in velocity divided by the time interval during which the change occurs, a equals vt 9. Instantaneous acceleration is defined as the limit of the average acceleration as the time interval t goes to 0, a equals lim v equals dvt 0 tons dt. The acceleration of an object at a particular time is the slope of the velocity time graph at that instant of time. For uniform motion, acceleration is 0 and the xt graph is a straight line inclined to the time axis and the vt graph is a straight line 54 physics parallel to the time axis. For motion with uniform acceleration, xt graph is a parabola while the vt graph is a straight line inclined to the time axis. 10. The area under the velocity time curve between times t1 and t2 is equal to the displacement of the object during that interval of time. 11. For objects in uniformly accelerated rectilinear motion, the five quantities, displacement x, time taken t, initial velocity v0, final velocity v and acceleration are related by a set of simple equations called kinematic equations of motion, v equals v plus at 0 x equals v0 t plus 1 2 at 2 v2 equals v0 2 plus 2 ax if the position of the object at time t equals 0 is 0. If the particle starts at x equals x0, x in above equations is replaced by x0. Motion in a straight line 55 points to ponder 1. The path length traversed by an object between 2 points is, in general, not the same as the magnitude of displacement. The displacement depends only on the endpoints. The path length, as the name implies, depends on the actual path. In one dimension, the two quantities are equal only if the object does not change its direction during the course of motion. In all other cases, the path length is greater than the magnitude of displacement. 2. In view of point 1 above, the average speed of an object is greater than or equal to the magnitude of the average velocity over a given time interval. The two are equal only if the path length is equal to the magnitude of displacement. 3. The origin and the positive direction of an axis are a matter of choice. You should first specify this choice before you assign signs to quantities like displacement, velocity, and acceleration. For if a particle is speeding up, acceleration is in the direction of velocity; if its speed is decreasing, acceleration is in the direction opposite to that of the velocity. This statement is independent of the choice of the origin and the axis. 5. The sign of acceleration does not tell us whether the particle's speed is increasing or decreasing. The sign of acceleration, as mentioned in point 3, depends on the choice of the positive direction of the axis. For example, if the vertically upward direction is chosen to be the positive direction of the axis, the acceleration due to gravity is negative. If a particle is falling under gravity, this acceleration, though negative, results in increase in speed. For a particle thrown upward, the same negative acceleration, of gravity, results in decrease in speed. 6. The zero velocity of a particle at any instant does not necessarily imply zero acceleration at that instant. A particle may be momentarily at rest and yet have non-zero acceleration. For example, a particle thrown up has zero velocity at its uppermost point, but the acceleration at that instant continues to be the acceleration due to gravity. 7. In the kinematic equations of motion EQ, 3.11, the various quantities are algebraic, i.e. they may be positive or negative. The equations are applicable in all situations, for one-dimensional motion with constant acceleration, provided the values of different quantities are substituted in the equations with proper signs. 8. The definitions of instantaneous velocity and acceleration, x. 3.3, and 3.5, are exact and are always correct, while the kinematic equations, EQ, 3.11, are true only for motion in which the magnitude and the direction of acceleration are constant during the course of motion. Exercises 3.1. In which of the following examples of motion, can the body be considered approximately a point object? A. A railway carriage moving without jerks between two stations. B. A monkey sitting on top of a man cycling smoothly on a circular track. C. A spinning cricket ball that turns sharply on hitting the ground. D. A tumbling beaker that has slipped off the edge of a table. 3.2. The position time, xt, graphs for two children A and B returning from their school O to their homes P and Q respectively are shown in Fig 3.19. Choose the correct entries in the brackets below. A/B, lives closer to the school than, B/A, B, A/B, starts from the school earlier than, B/A, C, A/B, walks faster than, B/A, D, A and B reach home at the same/different time, E, A/B, overtakes, B/A, on the road, once/twice. 56. Physics 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, 3.9, 3.10. Fig 3.19. A woman starts from her home at 9.00 am, walks with a speed of 5 km h1 on a straight road up to her office 2.5 km away, stays at the office up to 5:00 p.m., and returns home by an auto with a speed of 25 km h1. Choose suitable scales and plot the xt graph of her motion. A drunkard walking in a narrow lane takes 5 steps forward and 3 steps backward, followed again by 5 steps forward and 3 steps backward, and so on. Each step is 1 m long and requires 1s. Plot the xt graph of his motion. Determine graphically and otherwise how long the drunkard takes to fall in a pit 13 m away from the start. A jet airplane traveling at the speed of 500 km h1 ejects its products of combustion at the speed of 1500 km h1 relative to the jet plane. What is the speed of the latter with respect to an observer on the ground? A car moving along a straight highway with speed of 126 km h1 is brought to a stop within a distance of 200 m. What is the retardation of the car, assumed uniform, and how long does it take for the car to stop? Two trains A and B of length 400 m each are moving on two parallel tracks with a uniform speed of 72 km h1 in the same direction, with A ahead of B. The driver of B decides to overtake A and accelerates by 1 ms2. If after 50 s, the guard of B just brushes past the driver of A, what was the original distance between them? On a two-lane road, car A is traveling with a speed of 36 km h1. Two cars B and C approach car A in opposite directions with a speed of 54 km h1 each. At a certain instant, when the distance of is equal to AC, both being 1 km, B decides to overtake A before C does. What minimum acceleration of car B is required to avoid an accident? Two towns A and B are connected by a regular bus service with a bus leaving in either direction every t minutes. A man cycling with a speed of 20 km h1 in the direction A to B notices that a bus goes past him every 18 minutes in the direction of his motion, and every 6 minutes in the opposite direction. What is the period t of the bus service and with what speed, assumed constant, do the buses ply on the road? A player throws a ball upwards with an initial speed of 29.4 ms1. A. What is the direction of acceleration during the upward motion of the ball? B. What are the velocity and acceleration of the ball at the highest point of its motion? C. Choose the x equals 0 m and t equals 0 s to be the location and time of the ball at its highest point, vertically downward direction to be the positive direction of x-axis, and give the signs of position, velocity, and acceleration of the ball during its upward and downward motion. D. To what height does the ball rise and after how long does the ball return to the player's hands? Take G equals 9.8 ms2 and neglect air resistance. Motion in a straight line 57 3.11. Read each statement below carefully and state with reasons and examples, if it is true or false. A particle in one-dimensional motion, A, with zero speed at an instant may have non-zero acceleration at that instant. B, with zero speed may have non-zero velocity. C, with constant speed must have zero acceleration. D, with positive value of acceleration must be speeding up. 3.12. A ball is dropped from a height of 90 m on a floor. At each collision with the floor, the ball loses 1/10 of its speed. Plot the speed time graph of its motion between t equals 0 to 12 s. 3.13. Explain clearly, with examples, the distinction between a. Magnitude of displacement, sometimes called distance, over an interval of time, and the total length of path covered by a particle over the same interval. B. Magnitude of average velocity over an interval of time, and the average speed over the same interval. Average speed of a particle over an interval of time is defined as the total path length divided by the time interval. Show in both A and B that the second quantity is either greater than or equal to the first. When is the equality sign true? For simplicity, consider one-dimensional motion only. 3.14. A man walks on a straight road from his home to a market 2.5 kilometers away with a speed of 5 kilometers h1. Finding the market closed, he instantly turns and walks back home with a speed of 7.5 kilometers h1. What is the A. Magnitude of average velocity, and B. Average speed of the man over the interval of time, I. 0 to 30 minutes, 2. 0 to 50 minutes, 3. 0 to 40 minutes. Note, you will appreciate from this exercise why it is better to define average speed as total path length divided by time, and not as magnitude of average velocity. You would not like to tell the tired man on his return home that his average speed was 0. 3.15. In exercises 3.13 and 3.14, we have carefully distinguished between average speed and magnitude of average velocity. No such distinction is necessary when we consider instantaneous speed and magnitude of velocity. The instantaneous speed is always equal to the magnitude of instantaneous velocity. Why? 3.16. Look at the graphs, A, 2, D, Fig 3.20, carefully and state, with reasons, which of these cannot possibly represent one-dimensional motion of a particle. Fig 3.20 58 3.17 Figure 3.21 shows the xt plot of one-dimensional motion of a particle. Is it correct to say from the graph that the particle moves in a straight line for t0 and on a parabolic path for t0? If not, suggest a suitable physical context for this graph. 3.18-3.19 A police van moving on a highway with a speed of 30 km h1 fires a bullet at a thief's car speeding away in the same direction with a speed of 192 km h1. If the muzzle speed of the bullet is 150 ms1, with what speed does the bullet hit the thief's car? Note, obtain that speed which is relevant for damaging the thief's car. Suggest a suitable physical situation for each of the following graphs. Fig 3.22 Physics Fig 3.21 3.20 Fig 3.22 Figure 3.23 gives the xt plot of a particle executing one-dimensional simple harmonic motion. You will learn about this motion in more detail in Chapter 14. Give the signs of position, velocity, and acceleration variables of the particle at t equals 0.3 s, 1.2 s, 1.2 s. Fig 3.23 3.21 Figure 3.24 gives the xt plot of a particle in one-dimensional motion. Three different equal intervals of time are shown. In which interval is the average speed greatest, and in which is it the least? Give the sign of average velocity for each interval. Fig 3.24 Motion in a straight line 3.22 Figure 3.25 gives a speed-time graph of a particle in motion along a constant direction. Three equal intervals of time are shown. In which interval is the average acceleration greatest in magnitude? In which interval is the average speed greatest? Choosing the positive direction as the constant direction of motion, give the signs of v and a in the three intervals. What are the accelerations at the points a, b, c and d? 59 Fig 3.25 Additional exercises 3.23 3.24 3.25 A three-wheeler starts from rest, accelerates uniformly with 1 ms2 on a straight road for 10 s, and then moves with uniform velocity. Plot the distance covered by the vehicle during the nth second, n equals 1, 2, 3, versus n. What do you expect this plot to be during accelerated motion, a straight line or a parabola? A boy standing on a stationary lift, open from above, throws a ball upwards with the maximum initial speed he can, equal to 49 ms1. How much time does the ball take to return to his hands? If the lift starts moving up with a uniform speed of 5 ms1 and the boy again throws the ball up with the maximum speed he can, how long does the ball take to return to his hands? On a long horizontally moving belt, Fig 3.26, a child runs to and fro with a speed 9 km h1, with respect to the belt, between his father and mother located 50 m apart on the moving belt. The belt moves with a speed of 4 km h1. For an observer on a stationary platform outside, what is the a. speed of the child running in the direction of motion of the belt? b. speed of the child running opposite to the direction of motion of the belt? c. time taken by the child in a. and b? Which of the answers alter if motion is viewed by one of the parents? 3.26 Fig 3.26 Two stones are thrown up simultaneously from the edge of a cliff 200 m high with initial speeds of 15 ms1 and 30 ms1. Verify that the graph shown in Fig 3.27 correctly represents the time variation of the relative position of the second stone with respect to the first. Neglect air resistance and assume that the stones do not rebound after hitting the ground. Take g equals 10 ms2. Give the equations for the linear and curved parts of the plot. 60 Physics 3.27 Fig 3.27 The speed-time graph of a particle moving along a fixed direction is shown in Fig 3.28. Obtain the distance traversed by the particle between a. t equals 0s to 10s, b. t equals 2s to 6s. Fig 3.28 3.28 What is the average speed of the particle over the intervals in a. and b? The velocity time graph of a particle in one-dimensional motion is shown in Fig 3.29. Fig 3.29 Which of the following formulae are correct for describing the motion of the particle over the time interval t to t? 1 2, a, xt, 2 equals xt, 1 plus v, t, 1, t 2 tons, 1 plus, 1/2, a, t2 tons, 2 1, b, v, t2, equals v, t1, plus a, t2 t1, c, v equals, xt, xt, slash, tt, average 2 121, d, average equals, v, t2, v, t1, slash, t2 t1, e, xt, equals xt, plus v, tt, plus, 1/2, a 2 1 average 2 1 average, tt, 221, f, xt2. xt1, equals area under the vt curve bounded by the t-axis and the dotted line shown. Motion in a straight line 61 Appendix 3.1, Elements of Calculus. Differential calculus. Using the concept of differential coefficient or derivative, we can easily define velocity and acceleration. Though you will learn in detail in mathematics about derivatives, we shall introduce this concept in brief in this appendix so as to facilitate its use in describing physical quantities involved in motion. Suppose we have a quantity y whose value depends upon a single variable x, and is expressed by an equation defining y as some specific function of x. This is represented as y equals f, x, 1. This relationship can be visualized by drawing a graph of function y equals f, x, regarding y and x as Cartesian coordinates, as shown in Fig 3.30, a, b. Fig 3.30. Consider the point P on the curve y equals f, x, whose coordinates are x, y, and another point Q where coordinates are x plus x, y plus y. The slope of the line joining P and Q is given by tan equals yx equals y plus y, xy, 2. Suppose now that the point Q moves along the curve towards P. In this process, y and x decrease and approach 0, though their ratio y will not necessarily vanish. What happens x to the line PQ as y0, x0? You can see that this line becomes a tangent to the curve at point P as shown in Fig 3.30, b. This means that tan approaches the slope of the tangent at P, denoted by m equals lim y equals lim, y plus y, yx0 xx0 x, 3. The limit of the ratio y/x as x approaches 0 is called the derivative of y with respect to x and is written as dy/dx. It represents the slope of the tangent line to the curve y equals f, x, at the point, x, y. Since y equals f, x, and y plus y equals f, x plus x, we can write the definition of the derivative as dy dx equals df, x, dx equals lim x0 yx equals lim x0 f, x plus x, xf, x. Given below are some elementary formulae for derivatives of functions. In these u, x, and v, x, represent arbitrary functions of x, and a and b denote constant quantities that are independent of x. Derivatives of some common functions are also listed. 62d, au, equals a do dx dxd, uv, equals u dv plus v do dx dx dx, do equals do. dx dt dx dt, d, u slash v, dx equals 1 v2 do dx u dv dx. Physics do equals do dx dv dv dx d, sin x, equals cos x dx, d, cos x, equals sin x dx d, tan x, equals sec2 x dx, d, cot x, equals cos ec2 x dx d, sec x, equals tan x sec x dx, d, cos ec2 x, equals cot x cos sec x dx d dx, u, n equals n on 1 do dx, d, ln u, equals 1 do ud, eu, equals eu do. In terms of derivatives, instantaneous velocity and acceleration are defined as integral calculus. V equals lim t0 xt equals dx dt. A equals lim dt. Registered trademark 0 dv equals d2 x dt dt dt2. You are familiar with the notion of area. The formulae for areas of simple geometrical figures are also known to you. For example, the area of a rectangle is length times breadth and that of a triangle is half of the product of base and height. But how to deal with the problem of determination of area of an irregular figure? The mathematical notion of integral is necessary in connection with such problems. Let us take a concrete example. Suppose a variable force F, x, acts on a particle in its motion along x, axis from x equals a to x equals b. The problem is to determine the work done, W, by the force on the particle during the motion. This problem is discussed in detail in Chapter 6. Figure 3.31 shows the variation of F, x, with x. If the force were constant, work would be simply the area F, BA, as shown in Fig 3.31, I. But in the general case, force is varying. Fig 3.31 motion in a straight line 63 to calculate the area under this curve. Fig 3.31, 2, let us employ the following trick. Divide the interval on x-axis from a to b into a large number, n, of small intervals, x0, equals a, to x1, x1 to x2, x2 to x3. xn1 to xn, equals b. The area under the curve is thus divided into n strips. Each strip is approximately a rectangle, since the variation of f, x, over a strip is negligible. The area of the th strip shown Fig 3.31, 2, is then approximately ai equals f, 11, 11 11 1, equals f, 11, x, where x is the width of the strip which we have taken to be the same for all the strips. You may wonder whether we should put f, xi1, or the mean of f, 11, and f, xi1, in the above expression. If we take n to be very very large, n, it does not really matter, since then the strip will be so thin that the difference between f, 11, and f, xi1, is vanishingly small. The total area under the curve then is, NNA equals AI equals f, 11, xi equals 1 I equals 1. The limit of the sum as n is known as the integral of f, x, over x from a to b. It is given a special symbol as shown below, BA equals f, x, dx. The integral sign looks like an elongated s, reminding us that it basically is the limit of the sum of an infinite number of terms. A most significant mathematical fact is that integration is, in a sense, an inverse of differentiation. Suppose we have a function g, x, whose derivative is f, x, i.e. f, x, equals dg, x, dx. The function g, x, is known as the indefinite integral of f, x, and is denoted as, g, x, equals f, x, dx. An integral with lower and upper limits is known as a definite integral. It is a number. Indefinite integral has no limits, it is a function. A fundamental theorem of mathematics states that bf, x, dx equals g, x, bag, b, g, a. As an example, suppose f, x, equals x2 and we wish to determine the value of the definite integral from x equals 1 to x equals 2. The function g, x, whose derivative is x2 is x3/3. Therefore, 2x2 dx equals x332 equals 8313 equals 7311. Clearly, to evaluate definite integrals, we need to know the corresponding indefinite integrals. Some common indefinite integrals are 64. Physics xn dx equals xn plus 1 n plus 1, 1x, dx equals ln x sin x dx equals cos x x dx equals x, n1, x0, cos x dx equals sin x. This introduction to differential and integral calculus is not rigorous and is intended to convey to you the basic notions of calculus.